in this presentation, I've tried to cap the technicalities to a minimum, which means that I'm going to be a little bit sloppy with the math. So if you want clarifications of any kind, please don't hesitate to interrupt me and ask questions. So just to give an angle to this talk, what I'm going to discuss is ergodic theory for complex systems. So I don't think I need to convince you that we are surrounded by complex systems, so complicated systems consisting of different units interacting with each other. And so what I'm trying to do here is to study the statistical properties of the dynamics of such complex systems. And the statistical properties, I mean evolution of distribution of initial conditions, so evolution of measures with respect to the dynamics of these complex systems, and invariant physical measures, so equilibrium states for the systems. And I'm not doing this in any particular model, in any specific situation, but rather I'm considering abstract models that try to capture some of the properties of these systems, such as high dimensionality, intricate interaction structure, and chaotic behavior. And so this is not going to talk about reconstruction, but I think that, for example, from Thiago's talk today, it was kind of evident that knowing the ergodic property of a system can help us in the reconstruction problem. So one example of abstract models of a complex system that appeared at the end of the 80s is globally coupled maps. So here we have like a bunch of units interacting all to all. And each unit, the state of each unit is prescribed by a variable that I'm assuming to be one-dimensional, so it lives either on a one-dimensional torus or on an interval. And so the state of a network at a given time, it's prescribed by all of these coordinates that I can represent on one single copy of the phase space. And the evolution is given by this equation. So for each unit I, knowing the state of each unit at time t, I can recover the state at time t plus 1. And we already saw this kind of equation. And here the meaning is that f, the first function we apply, it's a local or uncoupled dynamics. So it's the dynamics that the system would have if we remove it from the network. And then we add up interactions, which are pairwise and additive in this case. So as I said, this appeared at the end of the 80s and was studied throughout the 90s and later. And most of the systems studied here, they had chaotic features. So there were maps taken from families, like the logistic family, or tent maps that are families whose maps exhibit some chaotic behavior. And the observations very soon showed different types of behaviors for these systems. One could observe, depending on the parameters and on the initial conditions, one could observe coherent states where all the units are grouped into a synchronized cluster, or some ordered phase where the units split in a small number of clusters, very large, or partially ordered where there is maybe a big cluster and then the other units are organized in smaller clusters, or they are just chaotic. And then there is a turbulent kind of behavior, or chaotic behavior, where this is very erratic dynamics and random-like. So this is kind of welcome because it shows that already a system which is not simple, but it has like simple equations and it has full symmetry, full permutation symmetry, already can exhibit quite diverse and complex dynamics, varying the parameters and varying the initial condition. What I'm going to focus on this talk is this case, the turbulent case, so the case where we are in some sort of chaotic regime. So one way that early on arose as a means of studying these systems is a thermodynamic limit. So let's take the size of the system to infinity and let's describe this limit. So again, these are the equations. To work out the thermodynamic limit, I go back to the finite dimensional system, and I describe the state in terms of a discrete measure, which is obtained as an empirical average of delta measures centered at the coordinates, at the variables for each unit in the network. So this is a sort of a pictorial representation of this measure, which is discrete. And now I can rewrite the equation with respect to this measure. And so the empirical average becomes an integral. And given the measure mu and t, it's a map that depends on the xi coordinate only. Of course, it depends on all the coordinates through the measure mu, but if we fix the measure, this is a one-dimensional map. So for now, I haven't done much. I just rewritten equations. But then, here it's how the measure evolves then from time t to time t plus 1. It's just the application of the push forward of this map to the measure. Push forward, which is indicated by the star, it's just given a map, it tells me how measures evolve. So if you have a distribution of mass, and this is made of like little particles, the map tells you how the particles evolve. The push forward tells you how the overall distribution evolves under the map. So now let's take the infinite limit. Then this, especially in the turbulent regime, in the chaotic regime, this is expected to converge to some measure, although this is an assumption, like I'm assuming that for some time t, this is converging weakly to some measure mu. And now this is what this evolution looks like in the continuous case, in the infinite limit case. And it's again a one-dimensional map that, given the measure mu, depends only on the coordinate of the unit. And this is the evolution for the measure in the thermodynamic limit. So it's application of the transfer operator of f mu t on mu t. So what have we gained here is that in the thermodynamic limit, this is a continuous distribution. So among other things, now we can deal with continuous measures with some smoothness. And so we can hope to analyze the system by using functional analysis. And this, in fact, has been done. And so just to recap what this object is that we are studying now, this thermodynamic limit. So we have a space of measures on a phase space, and we have a space of dynamical systems on that phase space. We have an application that takes a measure and associates a dynamical system. And then the main object of study, it's the application of the transfer operator associated with this dynamical system on the measure itself. So transfer operators are linear objects. But here, I'm applying a transfer operator on a measure, and the transfer operator depends on that measure. So this can introduce nonlinearities. So overall, this is a nonlinear object. And it's the object that describes the thermodynamic limit of the system. So one could ask, what are the fixed points of this operator, which would correspond to some stationary states in the thermodynamic limit, and what is the stability? If we start from a measure that's close to a fixed measure, does it converge to the equilibrium state or not? Then what is the stability of the equilibrium state under perturbations? So if we change the dynamics a little bit, does the equilibrium changes or not? So a linear response. All these questions have been addressed mainly in the setup where maps are uniform expanding and the coupling is weak. And crucially, it has been used the properties of the transfer operators, the contraction that these transfer operators have on suitable measure spaces. So for example, for example, if we take this system, these are coupled doubling maps with diffusive interaction and small coupling. One can show that if epsilon is sufficiently small, then this, the self-consistent transfer operator has a unique fixed point, which is Lebesgue. It's the uniform distribution. And the fixed point is stable in the sense that if we start from any other measure with sufficiently smooth density, under iteration of the self-consistent transfer operator, this will converge to mu. So mu is a stable point for the self-consistent transfer operator. And mu is also stable under perturbations. So if we tweak a little bit the coupling or the map, we will get an equilibrium state which is close to the uniform state. So far, so good. So this is one instance where the thermodynamic limit has been studied. But now the question is, what does the thermodynamic limit tells us about the finite dimensional system? Because so far, what we know is that if we fix a time window, we can find a system size sufficiently large so that the thermodynamic limit describes well the finite dimensional system within this time window. But we don't know what happens when we exceed the time window, so we could lose control. The thermodynamic limit might not match the finite dimensional system anymore. And in order to increase t, the only way we have is to increase n. Okay? So the question is, can we say something about all t's? So the motivation behind this question is that, of course, if you consider huge systems, like systems of the number of Avogadro of molecules, for example, then there is kind of no question that this is a good description. The thermodynamic limit is a good description. But if we consider systems which are made of a large number of units, but a few order of magnitudes less, is this description still kind of faithful or not? So it's more about now finding some quantitative dependence between t and n. Questions so far?
Or maybe just
the
left hand on your previous slide. So for fixed t and n large, this is just continuity.
Exactly, yes, it's just continuity. I'm not assuming anything more. And so further on, I will assume something more than continuity and try to exploit some uniform hyperbolicity. Yeah.
It's really just continuity because one measure is in one, the other measure is in another space.
It's continuity like in weak. So I was assuming that the convergence to the thermodynamic limit was weak. It's in weak topology. And then you have to assume something about the continuity of the maps. Yeah. I mean, you can always act on discrete measures. It's just you don't get, sorry?
A gap.
Yeah, exactly. You don't have a gap in this case, but it's again continuity tells you that you will be close if you consider the weak topology. So let's try to find a little bit more information about the thermodynamic limit in a hyperbolic situation, and more precisely when maps are uniformly expanding. So let me briefly recall what uniform expanding maps are. As the name gives away, these are maps that expand distances between points. So here I have 2 points, y and z. I apply the map f. Their distance is increased by a factor of at least sigma, where sigma is strictly larger than 1. These maps are examples of chaotic dynamical systems. They have all positive Lyapunov exponents. And they're fairly well understood. The general properties, I would say, they're fairly generally understood, or at least for uniform hyperbolic systems, maybe they're the best understood. And in particular, what I care about is that f, if this is uniform expanding and also has some degree of smoothness, f has a unique absolutely continuous invariant probability measure mu. And if you start from any measure having sufficiently smooth density, under iteration of the map, you will tend to converge to this unique measure. So, for example, if we consider a doubling map on a two-dimensional torus, and we start at time 0 with some mass distribution, then what the map does, it increases distances by a factor 2 uniformly, and then the mod 1 brings us back to the torus, so we have to cut and recompose the measure. So the measure gets smoothed out somehow. And if you keep iterating the map, you will eventually converge to the uniform distribution. This again has to do with contraction properties of the transfer operator for the uniform expanding map on certain spaces of measures. Another fact I care about for uniform expanding maps is their stability under perturbation, stochastic or statistical stability under perturbation. So if we take a perturbed version of the uniform expanding map F, and the perturbation is small and sufficiently smooth, then the new perturbed version will also have a unique absolutely continuous invariant measure, and it will be close to the original measure for the unperturbed map. Okay? So if we take, this say was the invariant measure for the doubling map, if we take a small perturbation of the doubling map, we will find, you cannot even see it here, but there was like a small difference here, a little bit more pion mass, but they are very close. Okay? So now, how can we reconcile this picture with coupled maps, coupled uniform expanding maps? So here I'm considering a map on the N-torus that has this form. So notice that I'm generalizing the setup a little bit with respect to what we are before. Now the local dynamics and the interactions, they are not identical. They can vary across the network. So there is no symmetry in the system. But I'm assuming that this defines a uniform expanding map. So this H, they cannot be too large. They don't have to be microscopical. It's not a perturbative result. You can perturb like order 1 and still get a uniform expanding map. And then so the objective is to study the evolution of measures under this map and characterize the invariant measure. The heuristic is the following. So this is the main argument, if you want. If I start from a product measure, this function here that prescribes the evolution of the ith coordinate, it's approximately equal to this expression where I substituted the empirical average with an integral with respect to the measure mu. This is not on the whole phase space, but it's on a big portion of the phase space with respect to the measure mu. And what I'm using here are concentration of measures results, analogous to concentration of measures for averages of independent random variables. And these, so these two are the empirical average above, it's approximated by the integral below, within a certain threshold. And what this tells us is that if we call this a mean field map, which is associated to the measure mu, then the actual dynamics, the coupled dynamics, it's going to be approximately equal in some sense to this uncoupled dynamics, which is determined by the measure mu. What this approximation means is the following. If you draw an initial condition with respect to the measure mu, and you look at the evolution of this initial condition by squinting your eyes, so by blurring the picture a little bit, you would not be able, with overwhelming probability, you will not be able to distinguish between f and f mu. Okay, so this is roughly what this is saying. You could be unlucky. You could be picking like an initial condition for which these two evolutions are very different. But the probability decays with an exponential of minus the dimension of the system. So now the question is, can we use this approximation to show that the evolution of measures under the coupled system, it's well approximated by the self-consistent transfer operator, which I'm defining here. Notice that the definition is basically the one I've given before. And in fact, here the setup is different. But if you start from a measure which has all identical factors and all identical local dynamics and interactions, this is the same definition as before. So it's just a little extension of the setup. And so does this self-consistent transfer operator, which is a sort of a thermodynamic limit, describes the finite dimensional system and to which extent? And what can we say then about the invariant measure of f, the absolutely continuous invariant measure of f, with respect to maybe fixed points of the self-consistent transfer operator? So with respect to equilibrium measures in the thermodynamic limit. So there are a few challenges that, I wanted to remark that this is the self-consistent transfer operator we have seen before. There are a few challenges that we are facing here. The main challenge is that the heuristic argument I've just shown relies on concentration of measure. So relies on the fact that I started with the measure mu that is a product. However, iterating the map f on the measure destroys the product structure. Due to the interactions, there is going to be dependencies among the units that start to build up. So we somehow have to find a way to control this map f also when the measure is not strictly speaking a product. The second challenge one faces is that perturbation theory in high dimension is kind of weird. And I'm going to give an example to explain why it's weird. And it's again one of the phenomena, it's the high-dimensional curse. We said that if f is smooth and uniform expanding, Then it has a unique absolutely continuous invariant measure that will have a density rho. We take a perturbation. This also will have an invariant measure with a density. And this density will be nearby. And will be nearby in terms of some very strong topologies on the space of measures. So there is going to be subnorm convergence when epsilon goes to 0, or L1 convergence when epsilon goes to 0. Now, let's use these two maps to construct high-dimensional dynamical systems. So we just take an n-fold uncoupled product of these two maps. Now, it's an exercise in ergodic theory to show that these two higher dimensional maps, they have absolutely continuous invariant probability measures, which are given by the product of the invariant measures for each single factor. So to find the invariant measure for this map here, you take the measure mu and you take the n-fold product. That's going to be invariant. What happens is that, and also, yeah, let me stress that we have two systems which are made of, each separately is made of identical factors. And these factors are nearby. These maps are nearby. So by most metrics, we would like these two maps to be nearby. And we would like the invariant measure to be nearby. However, if we consider these metrics here, the invariant measures, they become singular with respect to each other in the limit when n becomes large. So somehow the usual measures of distance between measures, it's not suitable for high-dimensional systems, at least at this level, in very general terms. So one has to deal with these somehow. And there's probably like many ways to go about it. One way, it's to try to define, and here I'm going back to something that also Thiago mentioned, try to define measures that are, in some sense, close to product measures, and try to measure how measures are close to product measures. So let me tell you the result. So here what I'm assuming is that the maps are all uniformly expanding. And in particular, if you look at the evolution on the height coordinate, and you assume that you fix the state of all the network but the height coordinate, this gives the evolution for the height coordinate. And I'm assuming that this is a uniform expanding map. Then I'm assuming that the interaction, they have bounded strength. So these function h, their norms, they don't depend on n. Okay, so I can increase n, and the strength of interactions scales as 1 over n. And here is the technical assumption, which I'm glossing over. It would be technical to write, but basically the expansion of these maps has to be sufficiently large with respect to E. So this means that E doesn't have to be small. That is not a perturbative result. But to have E order 1, you better have a large expansion. Then I'm also assuming that F has an attracting fixed point and that these are all absolutely continuous. So somehow we are in that situation I was describing at the beginning of the talk where there is a sort of a unique equilibrium measure in the thermodynamic limit. Okay? And now the result is the following. There is in fact a space of measures which one can say they are close to products, which are kept invariant by the dynamics, that if you pick one of these measures and you iterate the dynamics, this is what I'm doing. I'm taking push forward, or here there is a t missing. So this should be f star t nu. So I'm looking at any time t. And if I look then at the marginals of this evolution on each coordinate, the evolution of the marginals will resemble the evolution prescribed by the self-consistent transfer operator. So the evolution prescribed by the thermodynamic limit. And one can quantify how close these are in some metric, with respect to some metric that takes into account, it's like a soup distance over all marginals.
What is epsilon for you?
Epsilon? Oh, epsilon, oh, sorry. Here, epsilon is positive. It's just saying that we cannot really get to -1/2.
For any epsilon.
For any epsilon, yeah. Yes?
Your fixed point in, yeah, that's not, no, that's the first assumption for.
Yeah.
It's not product, it's just, you're just writing the marginals there, right?
I'm assuming, no, it's going to be a product also, because I'm assuming that these maps are all uniform expanding. So when you apply F, you apply a transfer operator for a product map. So somehow, if you start from a measure that's not product, application of F will make it a product. Yeah. Okay, so in a picture, so you start from a measure close to product, you iterate with the map F, the coupled map, it's going to stay close to a product. And under iteration, it will converge to the invariant measure. And if you look at the marginals will evolve accordingly to the self-consistent transfer operator, to the thermodynamic limit. And in the limit, the marginals will resemble the components of the fixed point for the self-consistent transfer operator. Okay. Right. So this is telling us that in the uniform expanding case, provided the expansion is sufficiently large with respect to the strength of the interaction, in fact, the thermodynamic limit gives a pretty faithful description of the system for all times. Now I want to say some of the main ideas to prove this theorem. The first is to define what some quasi-product measures are. So quantify what does it mean for a measure to be close to a product. And one way is to do it via these integrations. So we have Tn, the n-dimensional torus, and for every I, so for every coordinate, for every unit, I'm considering foliations into vertical fibers, like one-dimensional tori, which are just, you fix a point in all but the ith coordinate, and you build the fiber on top of it. Then one can take a mu and consider the disintegration with respect to this measurable foliation. Here, mu xi at is the measure that sits on the fiber xi at times t, and it's the conditional probability on that fiber. So these are all probability measures. If your mu has a density, which I'm assuming here, this is an expression for the density of the conditional probability measure. So you're just rescaling here. And the measure, it's quasi-product, if for every I, the density has some smoothness property, is log Lipschitz. For the experts, this lives in some cone of log Lipschitz functions. And the dependence of this density on the base point, so the dependence of the density on the fiber, it's Lipschitz. So as a map from Tn-1 to the space of measures, this is a Lipschitz function. And the Lipschitz constant, I'm assuming, is order n-1. So here we are taking a limit, right? So we're thinking of taking a limit. So I'm assuming that if I take the limit, this class of measures will have Lipschitz constant that it's a constant fixed, independent on the dimension, times n-1. So the first observation is, if L equals 0, this is a product measure. So this has to be for every I, right? So if L equals 0 means that there is no change in the conditional probability when you move from one fiber to the next. So this is a definition, yeah. Okay, no. It's going to be for every, actually, because I'm considering densities which are smooth. But it's true that for these integrations are not unique. They are defined up to negligible sets. So if you want, you can consider as, if you have any disintegration, you would take a smooth version. And then another important fact is that with this choice, these measures satisfy concentration. They exhibit concentration. So even if the measures are not products, there is some dependencies among the coordinates, but the dependence scales in the right way to lead to concentration results. So if you consider averages of an observable on T, where you evaluate the average at each coordinate, the probability with respect to mu that the average is away from the expectation more than epsilon scales as exponential of minus the dimension. And here the constant that you have here in this big O will present here at the exponent. Okay, so this is the main class of measures, and here I'm hiding a lot of details. It's a bit more complicated, the picture. So one thing I think I also have time I could mention is that, in fact, what you have to do, you have to take densities with a certain log Lipschitz regularity, and then measure the Lipschitz dependence with respect to a weaker regularity. So if these belong to a certain cone of functions, you measure the Lipschitz dependence with respect to a larger cone of functions, so with respect to less regularity. This is like some technicality, but just to like say that the picture it's a bit more complicated than what I'm selling here. Okay, so then what is the next step then is to prove that this class of measures is invariant under application of the coupled maps. And so the idea is the following. So we need to study the disintegration with respect to these straight vertical foliations. And so we want to find this disintegration, so information on this disintegration, the disintegration of the push forward of the measure, with respect to information of the disintegration of the regional measure. And we have to keep track of the regularity. So the Lipschitz dependence of these measures on xi has to be kept tracked by under push forward. So this is the picture at time, say, 1. And to figure out what the disintegration looks like at this time step, we need to figure out what the disintegration looks like at the previous time step with respect to the pre-image of the disintegration, a pulled back foliation. And here the pulled back foliation looks like this. You start from two fibers, you take the pre-image, you will have a lot of copies of the fibers here. And each blue copy here of weakly fibers will be mapped to the blue fiber, and each copy of the red fiber will be mapped to the red fiber. And if you put some conditions that involve expansion and interaction between the coordinates, you will know that these, you can prove that these are going to be tori. Okay? And so this, in fact, this pullback leads to a foliation, and the foliation is in tori, one-dimensional tori. Now we have to study how the disintegration with respect to this foliation translate with respect to a disintegration with respect to straight leaves. It's a sort of like vocabulary work we have to do. We have to switch between the two foliations. And the way I did it is the following. So one defines a global change of charts that straightened the leaves. And after this global change of charts, the dynamics becomes a skew product, where you are applying a map on each fiber when mapping the fibers to fibers. And the map depends only on the fiber. Okay? So it depends on the points on which the fiber is sitting. And then you apply another part of the dynamics that just tells you where the fiber is mapped to. And where the fiber is mapped to, of course, does not depend on the position on the fiber. So this is a skew product, skew product system. And then we keep track of regularity. So we start from a disintegration here with respect to vertical leaves, which has regularity L. So the Lipschitz dependence of this measure on xi has regularity L. The first step is to apply the change of coordinates. And the change of coordinates introduces a scaling factor in front of the Lipschitz constant. And the scaling factor is greater than 1, usually. So in these steps, the regularity, it's less. You get less regularity. The Lipschitz constant increases. And then you apply the maps. Unfortunately, it was color-coded, but it's not showing up on the screen. We have to first apply the map on the fibers, and then you apply the evolution of the fibers. And applying the map on the fibers, you gain a factor lambda, which is less than 1, that comes from the hypothesis on the uniform expansion, that tells us that transfer operators for uniform expanding maps are contracting. And so this contraction improves the regularity by this factor lambda. But then there is this shuffling of fibers and moving of fibers that could potentially spoil the regularity or not affect the regularity, but introduces a new factor kappa prime. And along the way, I also collected additive order n-1 factors, but then the condition is that the factor here in front is less than 1, and this gives me an invariant class of measures. And again, this condition here, there is this kappa and kappa prime that come from the interactions. The interactions large interactions can make kappa and kappa prime large numbers. And these large numbers, they have to be beaten by the contraction that comes from expansion. Okay, so this was the main idea. So let me just summarize. So what it was proved here is that uniform expanding coupled maps are well approximated by the self-consistent transfer operator or the thermodynamic limit, provided the main assumption is that expansion wins over interactions. And the main ideas were to use concentration of measures, which implies that for product measures or close to product measures, the maps you're applying or the transfer operator you're applying, they correspond to roughly uncoupled maps. And then study the invariance of measures close to products. And here, there was this study of evolution of these integrations of measures with respect to foliations that are not invariant. And I don't think we see this a lot in ergodic theory, in smooth ergodic theory. But it looks like it's almost natural in this context. And then prove that these quasi-product measures that one has defined that are kept invariant by the dynamics, they also provide concentration of measures. So this is more like a result in probability, if you want, where you're claiming that weakly dependent random variable with respect to the definition I've given of quasi-product maps, weakly dependent random variables, in this case, still exhibit concentration. So, and then some future work would be to estimate the transients when the assumptions are not satisfied. And also, so this is in one direction. It's still like a question in the thermodynamic limit problem. But then also another question is more general. Can we study self-consistent transfer operator in more general setups? So far, most of the results that give existence and uniqueness of fixed point for self-consistent transfer operators were either in situations where the self-consistent transfer operator is a nonlinear object, but it's very close to a linear operator. So there is weak interactions among the unit, or the case in which a self-consistent transfer operator it's very close to a map. And then you're only looking at measures which are very close to delta measures. And so the dynamics of the self-consistent transfer operator looks like a map. And then the question is going beyond the uniform expanding case. And so, for example, what we can say about uniformly hyperbolic systems, where you might have, in addition to expanding directions, you might have contracting directions. And this makes the description much harder because we cannot rely anymore on these nice spaces of measures which are contracted by the transfer operators. One has to go to a little bit more subtle objects, like anisotropic Banach spaces and more complicated cones of functions. Okay, that's it. Thank you.